Have you ever looked at a rational function graph and just thought, what is even going on here? Well, you're in the right place. Turns out they're all based on one single shape that just gets moved around. In the next few minutes, we're going to build the ultimate blueprint for these things, and you'll see just how simple they can actually be. But first, I've got a question for you. What on earth could this strange two-piece curve possibly have in common with one of the most powerful forces in the entire universe? Stick with me because the answer is actually pretty mind-blowing, and it connects this algebra concept right back to the real world. So here's our game plan. First, we'll meet the original, the parent function. Then we'll get into the invisible rules that control it. After that, we'll see it in action, moving it all over the place. We'll point out a couple of common traps to avoid, and then we'll bring it all home and see why this shape really matters. Okay, let's start at the very beginning with the parent function. Seriously, think of this as the master key. Once you understand this one single graph, you have the blueprint for basically every other rational function you're going to see. And this is it. Y equals 1 over x. It's called the reciprocal parent function. Every single one of those complicated-looking graphs is just a version of this one, maybe moved up or over or both. This is the original, the OG, the starting point for everything. Now, take a look at the shape itself. It's called a hyperbola, and you'll notice it's always in two separate symmetrical pieces. For the parent function, they live over here in the first and third quadrants. This whole two-part thing is the key to understanding everything else. All right, let's talk about the hidden rules of the game here. I like to call them invisible fences because they tell the graph exactly where it can, and more importantly, where it cannot go. Okay, so these fences are technically called asymptotes, and they're like invisible electric fences, right? The graph gets infinitely close to them. So close, but it will never, ever actually touch them. For our basic parent function, those fences are the y-axis, where x equals 0, and the x-axis, where y equals 0. Now for the really cool part. This is where the magic happens. We're going to start moving that blueprint, that original shape, all over the coordinate plane, just by tweaking the equation a little bit. Let's start with an easy one. We've got y equals 1 over x, and then a plus 3 just hanging out at the end there. So what do you think that little plus 3 tacked on the end is going to do? Yep, it's a vertical shift. That plus 3 is literally just an instruction telling us to pick up the entire graph and move it up 3 spaces. And the absolute first thing you want to do is move that horizontal fence, that asymptote, from y equals 0 up to its new home at y equals 3. And would you look at that? It's the exact same two-piece hyperbola. It just has a new center line. The whole shape is now built around that new horizontal asymptote at y equals 3. It's as simple as that. Okay, so that was easy enough. But what happens if we mess with the inside of the fraction, down in the denominator with the x? Let's check out y equals 1 over the quantity x minus 2. This one controls the horizontal movement. And here's the part that trips almost everyone up at first. That x minus 2 feels like it should move left, doesn't it? But it's the opposite. It moves the graph to the right 2 units. The trick is to think, what value of x would make that denominator 0? Well, x minus 2 equals 0 means x would have to be 2. And that's our new vertical fence. So check this out. It's the same exact hyperbola shape, but that vertical boundary line has just slid 2 units over to the right. And notice the horizontal asymptote is still at 0 because we didn't add or subtract anything outside the fraction. All right, you've seen a vertical shift, you've seen a horizontal shift. Now let's put it all together. You ready for this? This equation here has a change inside the denominator and a number hanging out on the outside. That means we're going to do both shifts at once. We literally just read the instructions right off the equation. Inside, the plus 1 with the x tells us to shift left 1 unit. Remember, it's the opposite. And on the outside, the minus 2 tells us to shift down 2 units. So we just move our invisible fences to their new spots at x equals -1 and y equals -2. And here's the big takeaway, the most important point. If you can find where the new asymptotes are, you found the new center cross for your graph. From there, you just draw the same parent shape. You can now predict exactly where any of these graphs will land. Okay, before you go off and become a graphing master, let's talk about 2 really common pitfalls. They are super easy to fall into, but just as easy to avoid once you know to look for them. Pitfall number 1, and I'm going to say it again because it's that important,
The horizontal shift is the opposite of what your brain wants to think. Just always ask yourself, what value for x would make the bottom 0? For x minus 2, that value is positive 2, so you shift right. For x plus 1, that value is negative 1, so you shift left. And the second pitfall, never, ever, ever, ever draw your graph crossing that vertical asymptote. Just don't do it. That line represents a value that is forbidden for x because it would make you divide by 0, which we can't do. It is a solid wall. The graph can get right up next to it, but it will never break through.
Okay, let's circle all the way back to the beginning. Why should you even care about this weird shape? What was that I said about gravity? Let's connect the dots. See, this shape isn't just some abstract thing in a math textbook. It is literally a blueprint for how the universe works. The force of gravity, how bright a light is as you move away from it, the strength of an electric field, they all get weaker with distance and they follow this exact same curve. So by understanding this blueprint, you're actually understanding the language of physics. So there you have it. You've gone from a strange-looking graph to a powerful blueprint that lets you understand a whole family of functions and even some of the fundamental rules of science. Now that you've got this blueprint in your tool belt, the only question left is, what are you going to master next?